All right. Well, good morning and welcome and happy Friday. And I hope you are doing well. So I posted. We graded your midterm exams, and I posted the grades, and you have seen them. And I don't know if your grade came in higher or lower than expected. Well, overall as a whole, the raw grades came in a little bit lower than I anticipated and I intended. So I applied an adjustment, and I just added 13 points across the board to everyone's score. So that pushed some students over 100%. That lifted up, other students, but everybody just kind of, I just slid everything over 13 points. So it's just a simple adjustment. I don't consider that a curve because it's not like I made sure this percentage got A's or this percentage got B's or this percentage got C's. Just kind of like just shifted up the median. But anyway, I want to always kind of take a moment and we'll go back to this kind of the very first day of class. I had this little section on grades in life, and I said, your grades do not define you. And I think now is a good moment to state that reminder once again. Whether you are happy with your grade or you are not happy with what happened, on the exam, I want to kind of take a moment and encourage a separation between your identity and your grades. I'll tell you a little story about myself, and I don't want to talk too long because I still want to make sure we cover floating point numbers because we got a lot to talk about there. But I think I can relate to a lot of students and this feeling of like I got to get good grades and stuff because in high school that was me. I worked really hard in high school to get good grades, and my senior year I applied to colleges, and I got into my dream school at that time, which was Caltech. So just a few miles away, and I thought I wanted to like study physics or space or something, and I got in. I was so excited, and I showed up in fall. They were also quarter system. And I went there, and like my very first quarter there, like I just couldn't handle the academic intensity. And so, my very first quarter there, I got my first C ever. And I thought, oh my gosh, like, okay, this was my first C ever, right? Because in high school it was like all A's, and like I had like one B, and I was like, oh, grr. But, and then, and then Caltech first quarter, fall quarter, I got my first C ever, and then winter quarter, freshman year, I got my first D ever, and then the path was already unrolling, and then spring quarter, like everything kind of fell apart. I failed multiple classes, and I got put on academic probation, and it was it was just kind of this culmination of like just all of this kind of stress and anxiety that I had kind of put on myself and was experiencing just because like every time, there was an exam or something coming up, I felt like, oh, I got to make up for all of this, poor performance that I had in the past. And it, and so, spring quarter, my freshman year, I failed a bunch of classes, put on academic probation. I was like depressed because I had tied so much of like who I was to my academic achievements and my academic performance. Because in high school, like I was not a star athlete. I was not like super popular or anything, but I had like for my comfort I had my grades, right? I was like, okay, well, I'm not going to parties, I'm not doing any of these fun things, but like look at this, I'm putting all of my energy into grades, and I've got good grades, and it seemed like it paid off because I got into my dream school, so I felt like it was okay. And then here I go to university, and like my grades are like total crap, and I'm like, okay, well, if I don't have this, like, what do I have, right? And so I felt like, just like, yeah, I felt totally like I was worthless at the time, but that was because, I tied so much of who I was to my grades. So, you know what, that summer after my freshman year, I didn't know what to do. I thought, the idea of returning to Caltech and like having to like earn a certain GPA to get off of academic probation before being dismissed, that was like overwhelming. The idea of like dropping out was like so like sad to me. And I was actually looking to kind of transfer to other schools, but I kind of missed a bunch of deadlines and stuff. So I'm very grateful. My parents, especially my father, was very supportive. And he basically told me, like, all this that it's putting you through, it's not worth it. The kind of this dream of going to Caltech and all of that, it's not worth it. And so I ended up dropping out at Caltech. There was like this little school in Michigan that was still accepting applications, and I said, hey, can I come? And they said, sure. And then so I ended up going over there. Kind of the change of scenery, I think, was good. And so things worked out, and like, so yeah, had to let go of my original dream, ended up going to the school I had never heard of before, finished my degree over there, and then came back to grad school later. Anyway, here I am now. At the time, it was a very painful experience, I wish, I have mixed feeling. Like, now that I'm so removed from it, I have, it's mixed emotions and mixed feelings about it. Because yes, it was very, very painful at the time. But also, I think what that experience taught me was I had to kind of separate myself from my grades, right? I had to find like who I was, find my value as a person, separate from my academic achievements. And I think that distance and that perspective has, greatly shaped, who I am today. And so, I don't view myself in terms of, no longer academic achievements, or even professional achievements. I find my kind of value as a person, based on, I guess, intrinsically who I am, my relationships with others. Also, my faith has also been important. But yeah, so anyway, all to say, I don't know where you are, and how, of course, it feels good to get good grades, okay? And it feels bad to get, a grade that you didn't want. And I understand, and I can completely relate. But, I do want to kind of just share this story and say your grades do not define who you are. You as a person are so much more than, whatever your academic achievements are, whatever your professional achievements. After you graduate from here, you're more than just a title and a salary, okay? You are like, you have so much more to offer to the world than just status, okay? So anyway, just wanted to share that with you. Anyway, that's all. As far as midterms go, if you want to just take a look and see, how it went, come by office hours. We'll pull out your exam, and you can take a look at it and everything like that. So, but yeah, wanted to share that story, and we'll look at floating point numbers now. Okay, all right. So we introduced floating point numbers on Monday. And we had the IEEE 754 specification for floating point numbers. This is how all of our computers store numbers. This is kind of this international standard for, how do we store basically numbers on a, binary system here. And so if we have a 64-bit double precision floating point, we have 1 bit for the sign, 11 bits for the exponent, 52 bits for the fraction. And, there's kind of these rules that we follow. And And to kind of understand and learn the rules, we're going to work with just like a miniature version of it, okay? We're going to have 1 bit for the sign, 3 bits for the exponent, 4 bits for the mantissa. And I think that, the smaller version will help reveal to us, kind of some of the interesting things that happen when you have floating point numbers, which, again, the key distinction between floating point numbers and real numbers is that there are only a finite number of floating point numbers, and so there is a lot of numbers just get approximated, and when you're dealing with approximations, there are funny little consequences. Okay, all right. So the sign bit 0 if it's positive, 1 if it's negative. We had 3 bits for the exponent, so this we covered on Monday, but it's worth kind of just briefly going over. So if we have 3 bits for the exponent, we are able to express a total of 8 unique values, and 2 of those values get reserved for special purposes. All zeros is special, all ones is 0. So we have 6 values left over. Half of those get used for positive exponents, 1 is for 0, and the rest are for negative. So we're able to express basically exponents from -2 to +3. And then the remaining 4 bits are for the mantissa. The mantissa assumes that there's a 1 in front of the dot, and then those four bits go here. And so, here's an example. I don't know, you guys want to try this out? See if you can translate and figure out what number this is, and then you can compare your results with your neighbor. I wonder if the answer is actually on. Not quite on the handout, but you can try this out. So try this out. You'll have problems like this in your homework 5. So how's homework 4 coming along? All right, well, I'm going to pause the video, and if you're watching the recording, you can pause too and try out this example. Okay, let's see what we got. Okay. So this first bit here, so the first bit is a 1, so that's negative. The exponent is 0, 1, 0. Okay, 0, 1, 0. In binary, that's equivalent to 2. And so we have an exponent of -1. Is that okay? And then the mantissa bits are the last 4, 1, 0, 1, 0. Okay? And so with the leading 1, we have 1.1010. Okay? So here I have 1 plus, this first spot is 1/2, this is 1/4, and this is 1/8. So I have 1 plus 1/2 plus 1/8, okay? Or basically 1 3/8, and we're going to multiply that by 2 to the -1, or 1/2, okay? And so, I'm sorry, 1 5/8. 1 5/8 is 13/8, okay? -13/8 times 1/2 gives me -13/16, okay? So in fraction, -13/16, or 26/30 seconds, and we're at 0.8125, -0.8125. Okay, I don't know if we got something kind of like that, but you can try that out. I guess another way you can kind of compute this out is rather than saying we have 1 plus 1/2 plus 1/8, you can roll the bit, right, binary point, over from 1.1010 to 0.11010, and then so that's 1/2 plus 1/4 plus 1/16, same thing, -13/16. We run into a problem though. With the current rules that we have, if we have all zeros, intuitively, we feel like this should represent the number 0, okay? But if we kind of look at our current system and our current rules, if we have the exponent bits are all 0, okay, then our exponent is -3. The mantissa bits are 0, 0, 0, and with the leading 1, we have 1.0000, and we would have 1 times 2 to the -3, we get 1/8. 0.125, right? Because we have, we're always assuming there's a leading 1. And if we always assume that there's a leading 1, there's actually no way for us to represent the number 0 in our current system with our current rules. And so in order for us to represent small 0 and other kind of numbers, we have something called denormalized mode. Okay, and so it was always kind of useful to kind of just assume that the leading digit in front of the binary point was a 1. Okay, and that reduces kind of any kind of redundancy because we don't need to actually store that. Okay, but yeah, again, we can't represent the number 0. So we have a special case for when the exponent is all zeros. Okay, so remember I said all zeros in the exponent is a special case. All zeros in the exponent mean we enter something called denormalized mode. And again, this is implemented in the IEEE 754 standard. So any system where you have all zeros in the exponent, you have denormalized mode. Okay, and to kind of prevent a discontinuity in the numbers, in denormalized mode, the exponent bias is going to be 1 less than usual. Okay, so in our mini floating point, the exponent bias is going to be only 2 when we're in denormalized mode. Okay, and then if we're talking about double precision floating point, the bias is normally 1023. In denormalized mode, it's only 1022. Okay, so all this to say is let's just revisit this. Okay, 0, the sign is positive 0. Okay, or positive for the sign bit. We have all zeros in the exponent. Okay, and so we have 0, 0, 0, and then again our exponent bias is 1 less than normal, so it's only 2. And so with a bias of 2, the exponent is going to be 2 to the negative 2. 2 to the negative 2. And when the mantissa bits are all zeros, and in denormalized mode, the leading digit is now 0. So we're going to have 0.0000 times 2 to the negative 2, which equals 0. Okay, so this is all just 0. Okay, it's a long way to arrive at what we intuitively kind of assumed, that all zeros would represent 0. Okay, before I forget, let me give you your first view quiz answer. Today's first view quiz answer is the letter A. A as in apple. A as in apple. The other special exponent case was when we had all 1s in the exponent. Okay, all 1s in the exponent, special meaning. You have infinity. You basically have all 1s in the exponent and all 0 in the mantissa bits. Okay, and so you have that's infinity, and then you can have positive infinity and negative infinity. Sign bit applies as usual. Okay, and then if you have exponent bits are all 1, and you have any combination of other than all 0. Any combination other than all 0 in the mantissa bits, then that's going to be not a number, the nan. Okay, the nan is, so there's going to be multiple, I guess, bit representations for nan, but we just say, yeah, all 1s in the exponent, anything other than all 0s in the mantissa will be nan. And we arrive at nan when we do something weird on the computer, like minus infinity plus infinity. Okay, then you're going to get nan. Okay, all right, so this is the smallest non-zero value that we can represent. So, or I guess the smallest positive non-zero element that we can represent. So we have all zeros in the exponent. The mantissa is 0, 0, 0, 1. Okay, so what does this correspond to? All right, so this, okay, is all zeros in the exponent. So this is denormalized mode. So our exponent is going to be 2 to the negative 2. We have negative 2. The mantissa bits are 0, 0, 0, 1. Okay, so this is the halves place, quarters, eighths, sixteenths. So we have 1/16 times 2 to the negative 2. 1/16 times 1/4. This is equal to 1/64. So in this miniature floating point system, the smallest number we can represent would be 1/64. What is the next smallest value we can represent? Okay, that would be this, okay? In binary, with the next value would be this place become a 1. And so here, this is 0, 0, 1, 0. This is 1/8 or 2/16, okay, times 2 to the negative 2, all right? And so this is 1/32 or 2/64. So our smallest value was 1/64. The next value is 2/64 or 1/32, okay? And then and then if we kind of keep going, then we go up to 3/64, 4/64, 5/64, 6/64. We're kind of incrementing our step size is 1/64 at a time, okay? And we can go all the way until our mantis bits are all 1s, okay? We're still in denormalized mode. Exponent bits are still 0, 0, 0. This is still, we're denormalized mode. 1, 1, 1, 1 is basically 15/16, right? 0.1111. So we have 1/2 plus 1/4 plus 1/8 plus 1/16. That's 15/16. And we multiply by our exponent, we're at 15/64. 15/64. And then what happens next? Okay, well, now we have a 1 here, okay? So this kind of like, if you didn't know anything about the floating point system, and you just said 1, 1, 1, 1, and then you go, okay, what's next in the thing? Well, what would you do? You would roll this up to a 1, and then these all become 0, right? It's kind of like the odometer, right? And then you do this, all right? And then what's the number there? Okay, well now our exponent bits are 0, 0, 1, right? And so now we're in normalized. This is regular old normalized mode. So now our exponent bias is 3, which is our usual bias. And so we do 1 minus 3. Our exponent is 2 to the negative 2. It's still 2 to the negative 2. Our mantissa bits are 0, 0, 0, 0. And then in regular normalized mode, we assume the leading digit is a 1. So we're at 1.0000 times 2 to the negative 2. And so we have 1/4, okay? And 1/4 is equivalent to 16/64. Right, so the previous number was 15/64, and now we're at 16/64, okay? And then what's the next number, all right? So if we add 1 to the mantissa here, okay, this becomes 1 and 1/16 or 17/16 times the exponent of 1/4. This is 17/64. So we're still counting up by 64ths, okay? So we got 15/64, and then so if we keep going, 18/64, 19/64, 20/64, 21, 22/64, and it keeps going until we reach all 1s here. And again, now we're at 1. This is normalized mode. And this is 0.1111, so plus 1/2, plus 1/4, plus 1/8, plus 1/16. So we're at 1 and 15/16 or 31/16 times the exponent of 1/4 or 2 to the negative 2. And so we're at 31/64. So far, so good? Okay, and this is also just kind of written out on your handout here. Okay, and then what is the next number? So again, we look at our bits here, and we go 1, 1, 1, 1, 1. Okay, and then so now this is going to become a 1. This bit here becomes a 1, and these all become 0s, right? So this is the next value here. And now what happens? Okay, and now our exponent is 0, 1, 0, which is 2 in binary. We have a bias of 3, so our exponent is negative 1. All right, so we're going to have times 2 to the negative 1 or times 1/2. The mantissa bits are 0, 0, 0, 0, okay? So the leading digit is a 1, and so we have 1 times 2 to the negative 1, or 1/2, okay? 1/2. And we've gone from 31/64 to 32/64, okay? Or 1/2. And this is, okay. So what do you think the next value is going to be? We're going to change this from a 0 to a 1. And the fraction, what do you think is going to be equal to? So we feel like, okay, we've been counting up by 64ths, so it feels like, okay, the next thing is going to be 33/64. But this is kind of the quote miracle of floating point things, okay, is that now that we have an exponent of -1 rather than -2, okay? When we increment this, what happens is we are now incrementing by 2/64ths or 1/32, okay? So let's look at this, all right? Our mantissa bits are 0, 0, 0, 1, okay? So when we look at this in normalized scientific binary, we have 1.0001, so that's 1 and 1/16. And then we multiply by the exponent, which is 2 to the -1, okay? And so this is 17/16 or 1/2, and we're at 17/32, all right? So we didn't go from 32/64, we went to 34/64, okay? And now our increment is not 1/64, our increments are now 1/32, okay? 1/32. And if we look at the next value, okay, the next value is this, and you can kind of go through, and this is now, so the previous number was 17/32, and now this value is 18/32, okay? If you go through it and you look at this, this is 1.0010, 1 1/8 times 2 to the -2, 9/16 or 18/32. And if you look at all of these, now we increment 18/32, 19/32, 20/32, 31, 21, 22. We're all at 1/32. Okay, and this keeps going until our mantissa bits become all 1s, and that is equal to 31/32. So now that our exponent is 2 to the -1, we're incrementing by 30 seconds. And then the next value will be 0, 1, 1, 0, 0, 0, 0, okay? And this, our exponent bits is 3. We have a bias of 3, so our exponent is 0. So this is 2 to the 0. So this is how we represent the number 1, okay? In this miniature floating point, this is how we represent the number 1. Okay, so this is the number 1. And what do you think is going to happen? If I increment this by the next value, I'm going to increment this by 1, what is this number going to be? It's going to be 1 and we'll just think, right? If I change this last bit from 0, 0, 0, 0 to 0, 0, 0, 1, it's 1/16 more, okay? So now we're going to go from 1, and the next number is going to be 1 and 1/16 or 17/16, okay? And then if I keep incrementing this, because now we're at 2 to the 0 here for the exponent, we're counting up by 16. So it goes from 1, 17/16, 18/16, 19/16, and we keep going until we reach 1, 1, 1, 1, which is going to be 31/16, okay, 1 and 15/16, okay? And once this fills out, it becomes, the next value is 2, okay? And at this point, when we increment, when we add 1 to this, now we're incrementing by 8s, okay? So we go from 2 or 16/8 to 17/8, 18/8, 19/8, all the way up to 31/8, okay? And or basically 2 and 15/8, all right? So right, this part counts, basically from, so if this is 2, and we're basically counting 1, 2, 3 up to 15, and each of these represent 8s. So we start off at 2 and we go up to 2 and 15/8. 2 and 15/8, 2 is 16/8. 16 plus 15/8 is going to be 31/8. Okay. And then this part, this now represents 4. Okay, right? So 31/8 is 2 and 15/8 or 3 and 7/8. Okay. This is now going to represent 4. 4 and now we're incrementing by quarters. 4 and 1/4, 4 and 2/4, 4 and 3/4, and then we go up to 4 and 15/4, which is such a weird thing to say, but 4 and 15/4 is going to be 31 quarters, okay? So 4 quarters is 16 quarters. 16 plus 15 is 31 quarters, right? 4 and 15 quarters, 4 and 15 fourths, okay, is 31 quarters, okay? And then what's the next value going to be? So after 31 quarters, we're going to add one more quarter to that, and that's going to take us to 32 quarters, or 8, and then now our step size is 1/2, okay? And then so I have 8 and 1/2, 8 and 2 halves, 8 and 3 halves, 8 and 4 halves, all the way up to 8 and 15 halves, which is, again, such a weird thing to say, but 8 and 15 halves would be, 15 halves is 7.5, right? 8 and 7.5 gives me to 15.5. Okay, so the increments here are now 1/2, and we get to 15.5. Okay, and then after 15.5, what happens next? Now my exponent bits become all ones. 1, 1, 1, 0, 0, 0, 0, and this represents the number infinity. Okay, so I mean, with this miniature floating point, we're not able to represent very big numbers, right? Like the very biggest number we can represent here before it becomes infinity is 15.5. Okay, so I mean, this is kind of a useless system for practical purposes, but that's the limitation of what we have here, right? If we're using 8 bits total, okay, we're able to represent numbers as small as 1/64, okay, 1/64. And then we can, we go 2/64, 3/64, and then we count up, and then the very biggest number we can represent is 15.5. And you say, I need to represent 20, and you go, nope, that's basically infinity for us, okay? It seems silly, but yeah, we go, okay, at 8, okay, and you can't represent 8.1 or 8.3 or 8 1/4. You can only have 8, 8.5, 9, 9.5. 10, all right? There's no number that exists between 8 and 8.5. You want 8 1/4? No, you cannot do that, okay? Not with the bits that we have. So, and it seems ridiculous, right? Because it's like, what good is this number system? Well, yeah, 8 bits, you can't represent very many values, and that's the limitation, okay? But so this is an interesting thing. And it kind of, like if you sit and think about it, it goes, oh, okay, that makes sense. But we can represent numbers. Over here we have no problem representing very small numbers: 1/64, 2/64, 3/64. We want to represent 1/4, no problem, right? You want to represent 2 1/4, we can do that. Okay. Where do we get to 2 1/4? Here's 2. Okay, 2 and 1/8, 2 1/4 is right here, okay? All right, you want to represent 2 1/4, that's no problem, okay? But once we get out here, you can't represent 8 1/4. It's either going to be 8 or 8.5, okay? And so, okay, this is my crude drawing, okay? But this is the number line, right? So you have really small step sizes, 1/64, and then once we reach to 1/2, our step sizes become 1/32, and then once we reach 1, our step sizes become 1/16, and then once we reach 2, our step sizes become 1/8. At 4, our step sizes are 1/4. At 8, our step sizes are 1/2, and then we get to 15.5, and then after that, it's basically infinity, right? So how far apart the numbers that we can represent on the number line depend where we are on the number line, right? So when we're close to 0, we can represent really small increments. As we get farther and farther away, basically at powers of 2, the steps in between numbers get bigger and bigger and bigger. Okay? All right, let me give you your second view quiz answer, which is the letter C. C as in cat. C as in cat. So let's look at specifics of double precision floating point. Double precision floating point, we have 11 bits for the exponent, 52 bits for the mantissa, okay? So to represent 0, we would have all zeros for all 64 bits, okay? We would have positive 0 is all zeros, and then technically you have negative 0 if you have a 1 for the sign bit, okay? But otherwise, you have 0 for everywhere, that's 0. Okay, what's the smallest non-zero, positive non-zero value we can have, okay? Well, we would have all zeros in the exponent, okay? And in denormalized mode, our bias is 1 less than normal, so we are at 2 to the negative 1022. We have 52 bits in the mantissa, and so the smallest non-zero value would be 51 zeros followed by a 1, okay? And that would be basically 2 to the negative 52. So the absolute smallest we can have would be 2 to the negative 52 times 2 to the negative 1022, which is 2 to the negative 1074. And you can represent this. You can type into R, and you can say, hey, what is 2 to the negative 1074? And it's going to say 4.94 times 10 to the times, e negative 324. If you ask, what is something smaller than this? We have no way to represent anything smaller than this value. This is the absolute smallest non-zero value we can represent, something on the order of 10 to the negative 324. Anything smaller than that is 0. So if I try 2 to the negative 1075, the computer says that's 0, okay? Which, we feel like, oh, this is small, that's pretty good, right? I mean, on the worksheet, the smallest number we could represent was 1/64. If we say, hey, how do I represent 1%? 0.01. Nope, that's 0, right? Anything smaller than 1/64 is basically 0, right? So there's nothing smaller than 1/64. And here there's nothing smaller than this number. And we go, oh, that's pretty small. But if you think about, like, on the real number line, this is very different from 0, but anything smaller than this is 0. There's infinitely many values between 0 and this number, but we can't represent any of those. Okay, what is the smallest normalized number that we can have? Okay, the smallest normalized would be having an exponent of all zeros with a 1 here, okay? So this is no longer denormalized mode. We have basically 10 zeros and a 1. That would be a normalized thing. So our bias is 1023, and our exponent would be negative 1022. And then our mantissa would be 52 0 bits, okay? And so here we have 2 to the negative 1022. 2 to the negative 22, and this is 2.2 times 10 to the negative 308, okay, approximately. And this value is known as machine x-min, okay? Or on our computer, it's machine double x-min. If there's ways to kind of talk about, what is kind of the smallest value your computer can represent in normalized mode, and it's basically in normalized mode, just all 0 bits, all right? And so we have 2 to the negative 1022. And so if you open up R right now and you type in .machine, it's gonna list off a whole bunch of stuff, and it's kind of just information about the number system on your computer, which and it's universal, because again, this is a standard, right? So you just type .capital machine and you can hit enter and a bunch of stuff. And one of the things will be double x-min, and this is basically the smallest normalized value you can represent. Okay, what is the second smallest normalized value we can represent? Okay, this is 1 point, and then the mantissa bits are all zeros, and we have a 1. Okay, all zeros, 51 zeros. So basically 51 0 bits and a 1, so that's 2 to the negative 52. So I can have x, which is machine double x-min 2 to the negative 1022. And then I can also do 1 plus 2 to the negative 52, okay? And we have, and this is a distinct value from this, okay? So the computer is able to distinguish between x and y. And if we print out all of the decimals, we can see, oh yeah, there is a very small difference, right? The last few digits are 72014, and over here I have 72019, okay? So the computer is able to distinguish between 2 times 10 to the negative 1022 and 1 plus 2 to the negative 52 times 2 to the times 10 to the negative 1022, okay? And so this concept of adding 2 to the negative 52 and the computer being able to distinguish this 1 plus this and 1 by itself, this is known as machine epsilon. It is basically, what is the smallest value you can add to 1 where the computer is able to distinguish this between 1 and this number, right? So this is known as machine epsilon. So it is, what is the smallest value that you can add to 1? So on our mini floating point system, what is our machine epsilon here? When we're using only 8 bits total and we have 4 bits for the mantissa, what is our machine epsilon? What's the smallest thing we can add to 1? Okay, so on the front page of the thing, you have 1, okay, 0, 0, 1, 1, 0, 0, 0, 0. And then on the next page, the next number that we can have is 17/16. Okay, so the smallest number we can add to 1 on this system is 1/16. Okay, 1/16. Basically, how many bits do you have for the mantissa? Here we have 4 bits for the mantissa, so we can add up to 2 to the negative 4, or 1/16 to 1. Okay, so on computers where we're using double precision floating point, we have 52 bits for the mantissa, so we can add up to 2 to the negative 52. Okay, that's the smallest thing we can add to 1, and it will be a distinct value from 1. Okay, so that's known as our machine epsilon. So we can add machine epsilon to 1, and the computer will recognize that these are distinct values. So we can say x is 1, and y is 1 plus 2 to the negative 52, and we can ask, is x equal to y? And the computer will recognize that they are not equal. It will say false. Okay? If you try to add anything smaller than machine epsilon to 1, the computer will not be able to distinguish those two values. So if I say a is 1, and b is going to be 1 plus 2 to the negative 53. So I'm trying to add something smaller than machine epsilon to 1. Okay? And if I say, hey, is a equal to b, to the computer, these two are the same. Okay? If I say b is 1 plus 2 to the negative 53, the computer is not able to kind of recognize that. Okay? So it's kind of like on your old school calculator. You can write 1, and then you can have like, I don't know, 0.0000, and then you run out of space. So if you try to add like, 10 to the negative 50 to 1 or something, you can't do it, okay? And here, if we try to add, 2 to the negative 53 to 1, we can't do it, all right? So the computer cannot distinguish between this and this. Yeah?
Would that be the same result for identical?
So identical checks numeric value, but also type. So like if you have a type integer, if you have like the number 2 in type integer, and then you have the number 2 in type double, identical will come back false. Okay, but if you have like 2 type doubles or something, basically it's asking, are these two things equal? But equal is going to just check for numeric values. Okay, so that's what we have here. Okay, so this is how we represent the number 1 in IEEE 754. Is basically our exponent is 0 and all 1s, okay? And then this part, the mantissa, is all 0s, okay? And so because this is 1023 in binary, 1023, and our bias is 1023. So this is going to how we represent the number 1. And so when we do 1 plus machine epsilon, the difference between this and this is basically I'm just incrementing the very last mantissa bit to be a 1. Okay? And so I think maybe this makes it a little bit clearer why we can't add anything smaller than machine epsilon. Because if I wanted to add something smaller than machine epsilon, I need more bits. I don't have anything beyond this. This is the 2 to the negative 52. This is the smallest thing I can add. So I can't add anything smaller than 2 to the negative 52 to this. Okay? All right, so here's a little thought experiment. Oh, we're gonna run out of time. Let me give you your last view quiz answer, which is the letter D. D as in dog. D as in dog. Okay? Let's say you started off this loop. You say x is 0, and then while true, which means run forever, do x plus 1. And you just let it run, right? You come back 10 years later. And you say, all right, computer, what do you got? What is x equal to? What do you think it's going to say? You feel like, oh, maybe it's reached infinity? Okay. No, it gets stuck, okay? It gets stuck at 2 to the 53. It gets stuck to 2 to the 53. All right, this is basically, this is the value 2 to the 53, okay? And so this is like very close to it. So here I have 9, I don't know, whatever this number is, 9007199, blah, 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 blah. Okay, I can add 1, and look, notice what happens to this last digit. We go from 990 to 991, and I say add 1 to that, and it becomes 992, and I say add 1 to that, and the computer says 992. It didn't change the value, okay? What's going on, right? But if I say, hey, add 2 to this, if I try to add 1 to this, it's stuck at 992, okay? But if I say add 2 to this, it goes, oh, okay, 994, right? And what's going on is basically we're at this point where we have a whole bunch of ones here, okay? This is kind of my my exponent, okay? And this is what my mantissa looks like, all right? And I'm sorry, not that. That's not what's going on, okay? But basically, we've come to a point where this is what we have, and this all fills up with ones. And then now, when I want to add something more, because my basically, remember, over here, our step size got bigger to the point where like we couldn't add anything smaller than like 1/2. Okay, basically, we're reaching a point where our step size has gotten bigger, and we can't add anything smaller than 2. Okay, and then as you go further up the number line, you won't be able to add anything smaller than 4, and as you go further up, you won't be able to add anything smaller than 8, and it kind of keeps going, right? And so it's weird, right? It's like, how can you say you can't add 1, but now you can add 2? It's just the step size. You've reached some point in the number line where the step size has gotten bigger. You can't add anything smaller than 2. You can't add anything smaller than 4, and this is that point right here. Okay. This is the largest possible value that we can represent that is not infinity. This is known as machine double X max, okay? And it's basically all ones in the mantissa, and then basically the exponent is almost all ones, right? But it's not. All ones would be infinity or nan. And so this is the absolute largest value we can represent. And that's around 10 to the 308, which is a pretty big value, but also a far cry from infinity. And again, just like the mini floating point, the largest number we could represent was 15.5. This is the largest number we can represent. Anything bigger than this comes back as infinity, okay? And so here, if I do at this point, at this point, the increment, the step size is 2 to the 970th power, right? So you think, what is a big number? Is 2 to the 969 a big number? It is a big number. In comparison to this, though, it's not. And so if I say, here's A, this is my number, and I want to add 2 to the 969, the computer isn't able to do that, okay? I say, A is this number, X is A plus 2 to the 969, and it says, oh, you know what, A and X are the same. You say, I just added 2 to the 969. That's a huge number. And the computer says, no, it's the same. They're the same to me, okay? So then you say, all right, well, add 2 to the 970th, all right? And then the computer says, oh, whoops, now it's infinity, okay? Now it's infinity. We can't add anything bigger than this, right? So it's like weird stuff, right? So, okay, so going back, we saw stuff like 0.1 plus 0.2, is that equal to 0.3? And it's not, okay? So what we can do, like there's a function called all equal. This is all equals a misnomer. It should be known as like nearly equal. Are these things almost close to each other? And then it'll come back true, right? There's a thing though, right? Like remember when we did 10 divided by 3 on the old calculator and we got 3.33333? Like what if you actually wanted not 10 thirds, but you actually wanted the value 3.333. right? You won't be able to know the difference between 3.333 and 10 thirds, right? And that's one of the consequences here. Well, anyway, this is what happens when you do all equal, and it will say, yeah, these things are equal or these things are different, and it can't really tell the difference there. Okay, there's a issue known as catastrophic cancellation. I won't test you on this, but it's good to know about, and it's basically like because of floating point, stuff breaks and goes wrong. Okay, sorry for going over my time, and thanks for listening to my story this morning. But have a great weekend. Enjoy your Monday off, and we will see you on Wednesday.